Before we get into double integrals, I'd like to remind you of what you likely saw regarding single integrals. You were probably presented with the problem of finding the area under a curve f over the interval from a to b, and that area was approximated by summing up the areas of rectangles. If we consider an element in the ith subinterval to be x sub I star, and the function height at that value as f of x sub I star, then that function height would give the height of an approximating rectangle. The width of such a rectangle is typically given to be delta x, and so the area of the ith rectangle is going to be f of x sub I star times delta x. That would be the height times the width. The actual area under the curve would be given by the integral from a to b of f of x dx, and that's the limit as n approaches infinity of the sum as I goes from 1 to n of f of x sub I star times delta x, letting the width of each rectangle go to 0 and summing up an infinite number of such rectangles. To translate this to R3, we're going to use a textbook image. And here we have a portion of a surface over a rectangle in R2. That rectangle in the xy plane is defined by an interval on the x-axis from a to b, and an interval on the y-axis from c to d. So the rectangle is given by the closed interval from a to b by, it looks like times, the closed interval from c to d. You can see there's identified a rectangle within this region, and it's given by Rij, and what this is indicating is that it's in the ith subinterval on the x-axis between a and b, and the jth subinterval on the y-axis between c and d. An element within that ijth rectangle is x sub ij star, y sub ij star, and the function evaluated at that input is going to give the height of a column, which is a rectangular solid. Here we're going to say that the volume of the ith column is equal to f of xij star yij star, that's the height, times delta area, where delta area is the area of the rectangle in the xy plane. The volume under the surface and above R in the xy plane is V is equal to the limit as mn both go to infinity of the sum as I goes from 1 to m of the sum as j goes from 1 to n of f of x sub ij star y of sub ij star times delta a. This is expressed as a double integral. Volume is equal to the double integral over the region R of f of xy dA. To see what's going on with the limit, I have a series of diagrams for you. In these diagrams, what's depicted is the area under a surface z equals 16 minus x squared minus 2y squared above the first quadrant. So this surface is in the first octant. And you can see that using 4 rectangles, we kind of miss a lot of the space. And the approximation using the columns gets better and better as the number of rectangles increases. And of course, if we take the limit as the number of rectangles goes to infinity, then we end up with an accurate number for the volume. Pretty much what you'd expect by extending what you knew from R2 into R3. But then the question arises, how do we compute such an integral? That leads us to our first example, the integral from 0 to 1 of the integral from 0 to 1 of x plus y, the quantity squared, dx dy. Now that dx dy is the dA, the dA here, and it comes from the delta area here, and it comes from the idea that the rectangle r sub ij in the xy plane has dimensions delta x by delta y. Well, back to our integral. The way we're going to compute this is we're going to treat the inside integral as though it were something from first semester calculus. That is to say, the order in which dx dy is written indicates the order in which we're going to integrate. The innermost integral corresponds to the innermost differential, so in this case dx. The outermost integral corresponds to the outermost differential, and in this case dy. When we actually integrate x plus y, the quantity squared, with respect to x, we're going to consider y to be a constant. So in a sense, this is like partial integration, just like in partial differentiation when we hold all but one variable constant. So this is written as the integral from 0 to 1 of, now applying the power rule, yes, to x plus y, the quantity squared, we get 1/3 times x plus y, the quantity cubed. Now the question is, what do we do with the limits of the innermost integral? Well, we tack them on here. We're going to evaluate 1/3 times x plus y, the quantity cubed, from x equals 0 to x equals 1. We still have the outer integral, and it needs to be integrated with respect to y when we're done, so I still need to write dy. Evaluating the integrand now at the limits for x, we have 1/3 times the quantity of 1 plus y cubed minus y cubed, and we're going to integrate that with respect to y. We could expand the 1 plus y quantity cubed and collect like terms, but the power rule applies here, so we'll just use the power rule. You'll confirm, I'm sure, that this turns out to be 1/12 times the quantity of 1 plus y, the quantity to the 4th power, minus y to the 4th, evaluated from 0 to 1. This will give us 1/12 times the quantity of 16 minus 1 minus 1. The 16 minus 1 coming from evaluating y equals 1, and the 1 coming from evaluating y at 0. At the end of the day, this turns out to be 7/6. Now, I neglected to write down the instructions at the outset of this exercise, so I'm going to do so now, mostly because I want to give you some vocabulary. The instructions for this exercise would be calculate the iterated integral. And we did it in iterations, right? We integrated with respect to x first, and then we integrated with respect to y.